So, somewhat recently, there was a experiment that was done that basically what they did was they shot like um, photons at a material. I guess maybe like a thin sheet of material, very small amount of the material, right? And so they shot photons at this material, and um, as they what they observed when they like watched it the photons interact with this material is basically that it appears as if the photons are coming out the other side before they've even really entered, right? And this is, bizarre. It's like, okay, well, um, why is that happening, right? At first they were like, oh, it's a mathematical fluke, it's not real. But then they like basically tested it, and they were able to do an experiment where, they observed it happening in, reality, not just in the mathematical world. And so they were like, okay, well, I guess it's not just some mathematical fluke. This is real. This is actually a real phenomenon, right? And so their assumption from this data is that basically time, it's negative time, or something along those lines, where basically, like because of quantum mechanics and stuff, it doesn't like basically one of my pet peeves with quantum mechanics is that every time something weird happens and we don't know an explanation, we just go, I don't know, quantum mechanics is weird, am I right? And I really don't like that because it's so hand wavy. We just say, oh wow, quantum mechanics is just so hard to understand and so weird. We just don't get it. And it really makes it so easy to give up on finding a solution. And I don't like the whole negative time thing. But so what I wrote here is I think that the actual solution to this problem isn't negative time. It's not that photons are experiencing negative time, right? That doesn't really make sense to us. And the reason why it doesn't make sense is because I don't think, like, the reason why there's no logical framework for that is because we don't see it happen. And I realized that I didn't turn off my air, and that would have been annoying if it kicked on. So, and so we don't, we don't observe negative, like, that opens up such a can of worms, because when do photons experience negative time? Is it always only in niche scenarios? Like, where do you draw a line with that? That doesn't, like, that opens up such a large can of worms with no good explanation. The better explanation is it's not that, right? And so, while I do agree time is relative and that smaller particles move faster because of their smaller size, I am not certain that is what we are seeing here, right? So basically what I believe is that, there's a potential that the speed of light that we observe is really, it's not real. Like, we couldn't actually achieve that speed. The reason why that speed is that fast is because, one, it has a lot of energy and it's moving quickly, right? But it's also time dilated because its scale is smaller. So what we're watching this thing fly by, right, at the speed of light, it's going so fast. But what is traveling a distance of 1 meter, right, is taking it potentially billions of years to travel that distance. But for us, it's nothing, right? And so we look at it and we go, wow, it moves so fast. And I don't know if that's necessarily real. I don't know if that's actually what's happening there. And I could be wrong about that, but I think on some level, time is distorting what this speed truly is. And so the smaller the particle is, it's in a smaller scale, its time is warped. And so what we perceive as things moving really quickly may not actually be as quick as you think. It's just that there is a relative time difference between these two things, right? And so I think that something like that can be happening, but that still doesn't bring about negative time, right? So again, I don't think that's what we're observing here. And so I may be misunderstanding what they observed, but in my theory, space is a fluid, and when moving through a fluid, you create ripples as you bunch up the fluid in front of you, right? So if you fill a bowl up with water, right, and then you put your finger in the water and move it, across, you'll notice that you get the ripples will there's a mini wave that piles up in front of where your finger's actually at, right? So it's not that the weight, the water doesn't just bunch up on your finger, but you also get a secondary ripple out in front. And this is because as you're pushing, right, you got to push the water that's in front of you out of the way before you can take up the space the water is occupying, right? And so in order to do that, you kind of have to bunch it up. And since you're pushing it forward, right, then it collides with other stuff, and there's a little bit of an acclimation period before the stuff can move out of the way. It first has to run into other things to tell them, hey, get out of the way, right? So you get this kind of bunching up effect happening in front of you, and then off to the sides and stuff, things bunch up still, but then it slowly dissipates out, and that's what we see as waves, right? And so again, this gets back to my theory about electromagnetic radiation and how magnetic waves are really just these bunched up ripples that are caused by these photons basically doing that, right? And believe me or not, I recently just looked at it. I only have 50 views on the video, and I have one dislike, and I think it's so funny. Yeah, but and so anyway, right, so you get this kind of bunching up kind of in front, and so you have a consolidation of energy right in front of the actual photons themselves. And so this is akin to, before the explosion actually hits you, there's a shock wave that comes out, right? You get hit by the shock wave, and then boom, then the explosion hits you, right? And so what I think may be happening here is that the shock wave basically of these photons is penetrating and then exiting this material before the photons reach it, and they're observing this energy shift, and they notice, hey, when the photons come out the other side, they're coming out before they actually enter, but they're also at a lower energy. And I think this is why, is because it's not actually the photons, right? The photons are not losing energy, and going in negative time and then losing energy. It's that it's not actually the photons that they're observing here. There's energy there. It's an accumulation of energy, but this also gets into, dark energy being basically this fluid that's all around us, which is also not a current well-established belief. And so, this ties in a lot of concepts here, because we're working on this smaller scale, and I'm slowly trying to unravel who knows what's happening with quantum mechanics, right? By actually giving explanations, by actually defining principles here, by, unraveling the uncertainty of every interaction, because I feel like it's just so, I'll never understand quantum mechanics because it just doesn't make sense. And it's what kind of science is that, right? What kind of science is that? Anyway, and so, right, basically, I think that we have a shock wave of virtual particles that is caused by the photons themselves moving in a direction, right? And this is, exciting the atoms. It's causing a excess of energy it's causing, a consolidation of energy to kind of lead the charge, basically, so to say. And it's most noticeable right after it comes out of the materials, because that's where there is the most, like, it's the most densely compacted matter, right? Because in the air, it's very easy for this energy to be dissipated, right? You don't notice, like, when I punch, right, you're not hearing like me hit anything, right? And you're not seeing anything happen. But if I had a board in my hand or something, right, you would hear me hit the board, right? And you would see my hand move, right? You would see that happen because there's more matter there, right? But when I'm punching the air, nothing happens. Like, you don't notice anything happening. So this is what I think is also happening again with this, these photons, right? Basically, the shock wave that's in front of them is impacting the material and coming out the other side. And we're seeing potentially even just like the excess oscillation vibration from the material itself being hit by this shock wave, right? It's not even the shock wave that's coming out the other side. It's the reaction to the shock wave that is coming out the other side. Can I prove this? No, because I'm not doing the experiment, but this is my potential theory here. And it's a lot better than negative time, because negative time breaks so many things. Why would we just constantly want to break everything? Why are we breaking everything and saying, oh, I don't know, it's weird, right? It's terrible science. I feel like some people are just excited to make weird discoveries, right? But it's like, okay, but what does that really mean? What does that really mean, right? And so I don't know. I don't like it. Maybe I'm wrong. Maybe negative time is totally a thing, and quantum mechanics is just as weird as everyone says it is. But until I find definitive proof that I can look at and be like, okay, there's no way I can refute this. Yes, it really is that weird. I'm not gonna, right? So I don't know. Peace out.